So continuing with coherence, which is the property we were looking at, lasers are highly coherent. That is a characteristic property of laser. Why so? Mainly because of stimulated emission. So when we were looking at intensity, we saw why intensity is because of the repeated amplification. So it is an inherent characteristic of the repeated amplification process is that it produces waves with high intensity. Similarly, an inherent characteristic of the stimulated emission process, the process which is responsible for giving birth to the photons in the first place, is that it produces highly coherent waves. Now why so? We will learn when we look at stimulated emission, of course. So right now all we need to remember is that laser light is highly coherent. Now there are two types of coherence, spatial and temporal. Coherence, spatial is coherence between waves at 2 points in space perpendicular to the direction of propagation at the same time. So it is a slightly complicated looking definition, but we will try to understand with the help of this example. Imagine a bunch of let's say NCC cadets performing a march past. They are arranged in rows and columns, and here in the context of the march past, coherence would be defined as the coordination or the sync between the different cadets. So when someone puts their right foot forward, everyone in the same row should put the right foot forward, and when someone lifts their left arm, everyone should lift the left arm. That sync is what we call coherence in this analogy. So what is spatial coherence is coherence between waves at 2 points in space perpendicular to the direction of propagation at the same time. So the direction of propagation is, let's say they are moving in this way, as in they are moving from the back to the front in the picture. Then perpendicular to that would be the row, right? So this in this direction. So because it's a two-dimensional plane, it's not easy to show the axis, but I'm sure you can visualize. So they're moving from here to here, and this row is the perpendicular direction. So coherence between 2 points in this direction at the same time, meaning coherence between two cadets on the same row. So between, let's say, the first young man and the second young man, are they both in sync with each other? That is spatial coherence. So similarly for waves, when you take two waves which are perpendicular to the overall direction of propagation, and are they both coherent? How do you define coherence among waves? Same frequency, same or different, same or constant phase difference. So let's say these are waves. In this part, ignore the people in the picture, just look at the curves. Each curve represents waves. So the direction of propagation is from left to right, let's say. So let's say this is one wave here and this is one wave here. Are these two waves coherent? Do these two waves have the same frequency, and is their phase difference zero or constant? That is what we mean by spatial coherence. Temporal coherence, on the other hand, is coherence between two waves arriving at the same point spatially at different times. So this person is at this point, let's call this point X. This person is at this point X right now. So after this row marches forward, the second row will occupy this position, and then this person will be at the same point X. So is there coherence between these two young men? So when this person came to point X, he had, let's say, right arm and left foot forward. So when this person comes to point X, he should also have his right arm and left foot forward. So similarly, extending the same to our wave concept, this wave is at the point x2 right now, and it has a certain frequency and a certain phase. Now when this wave comes to x2, does it have the same frequency, and is the phase difference zero or constant? That is what temporal coherence refers to. So those are the two types of coherence. Spatial is at the same time between two different positions. Temporal is same position, two different instances of time. These are just a list of experiments which can be used to study coherence. For spatial coherence, we have the YDSC. For temporal coherence, we have these. You can just go through the names. There's nothing much here. You don't need to know the experiments themselves as such. Okay, now coherence time. Okay, so coherence time is something like a quantitative measure for coherence, not exactly for coherence, but for the time period up to which the source remains coherent. So let me explain. Again, when we look at a laser or any source of light, it emits a beam of light. A beam is made up of a number of rays. So each ray we can think of it as a wave also, because of the wave particle duality, which all of you are familiar with. Now, so basically my light source is made up of a bunch of waves. So when they start out, when I switch on the source, they are all going to start, let us assume, with the same frequency, same phase, meaning they are coherent. But they will not remain coherent throughout the time period for which the wave travels. Only for a short period of time will they remain coherent, as in the frequency will remain the same. So if I say the frequency is so many hertz, it is going to remain as many hertz throughout. But the phase difference changes because of a number of factors. So because of small particles in the air with which the beam will interfere, because of interference with other waves, and because of a variety of reasons, the phase is going to change. And when the phase changes, the phase difference need not remain constant, so the different rays need not remain coherent. So when I switch on the source of light, for a short period of time, the waves remain more or less coherent, as you can see over here from the graph. After that, they might or might not remain coherent. So that time duration for which the source remains coherent, or the time duration for which phase correlation exists between the photons, is called coherence time. And coherence time is inversely proportional to the frequency width. So we looked at frequency width when we were doing this property called monochromaticity. So here we see that coherence time is inversely proportional to monochromaticity. So the more monochromatic your light is, the lesser the coherence time is going to be. And coherence length is the distance travelled by the wave during its coherence time, meaning let's say my wave or my source remains coherent for 5 nanoseconds. What is the distance it covers in that 5 nanoseconds? Because the wave is travelling, right? So it is travelling in space. This is a light wave. It is travelling from the source to some wall or whatever I am shining it on. So within the time duration for which it is coherent, what is the distance it covers? That is the coherent length. Length is again, distance is given by speed into time. So coherence length is velocity into time, speed of light into coherence time, which is c divided by delta nu. So here we take the proportionality constant as equal to 1. So coherence time tau is equal to 1 upon delta nu, and coherence time LC is c divided by delta nu. So that is it. To quickly recap, we looked at coherence. Two types of coherence, spatial and temporal. Spatial is coherence between two waves along the same at different positions along the same axis at the same time. Temporal is at the same position at two different units of time. And then we looked at coherence time, which is the time duration up to which the different rays of light in the source remain coherent, and the distance travelled within that time duration is coherence length. So to sum up everything we have seen so far, laser stands for light amplification by simulated emission of radiation. Simulated emission is responsible for giving rise to the photons. Repeated amplification is responsible for making sure the photons are not lost and for maximizing the intensity. And the properties of a laser are high intensity, high directionality, high monochromaticity, and high coherence. So that was an introduction to lasers. In the subsequent classes, we will be looking at simulated emission and different types of lasers and so on.